Hello, I am Heeyeon Kim from KAIST, Department of Industrial Systems Engineering, DISL Lab. Today, I will be presenting a review of the paper on Improved Distribution Matching for Dataset Condensation, CVPR 2023. Before diving into the details of the paper, let's first take a look at what dataset condensation is. Dataset condensation, also known as dataset distillation, is a training set synthesis technique for data-efficient learning. It learns to condense large dataset into a small set of informative synthetic samples for training deep neural networks from scratch. The following images are examples of synthetic images, which are generated through dataset condensation from the CVPR-10 dataset. The original dataset consists of 50,000 images, with 5,000 images for each of the 10 classes. The new synthetic set was generated with either 1 or 10 images per class, as shown below. The goal of the dataset condensation is for the model trained on 50,000 images, as shown on the left, to achieve similar performance to a model trained on just 10 or 100 images, as shown on the right. Dataset condensation techniques can be categorized into 4 main approaches. The first is metamodal matching, which ensures that the performance of a model trained on the large original dataset is similar to that of a model trained on the condensed synthetic dataset. The second is gradient matching. This technique generates a synthetic set by reducing the distance between the network trained on the large dataset and the one trained on the synthetic dataset. The third is trajectory matching, where the synthetic set is created to follow the training trajectory of the model trained on the original dataset. Lastly, distribution matching focuses on making the data distribution of the synthetic set similar to that of the original dataset. I will now introduce the paper, Improved Distribution Matching for Dataset Condensation, which advances the fourth technique, distribution matching. Next, let's take a closer look at distribution matching. According to dataset condensation with distribution matching is a technique that matches the distribution of embeddings between real and synthetic datasets. Dataset condensation proceeds by matching the mean of the embeddings from the real dataset with the mean of the embeddings from the synthetic dataset. Synthetic data are optimized by using the maximum mean discrepancy. Unlike other condensation methods, distribution matching techniques are much faster because there is only one element to match. However, their downside is that they tend to have lower accuracies. In this paper, they introduced 2 shortcomings of distribution matching. First, there is an imbalance in the number of features between tau and S, so the performance of distribution matching is inevitably lower. Distribution matching aims to match the feature distribution of tau with that of S, but the size of tau is much larger than S. However, due to the large difference in size, it is impossible to match the feature distribution exactly. Distribution matching works well if and only if the large number of features extracted from tau can be well approximated by the small number of features extracted from S. The second shortcoming concerns the unvalidated embeddings in MMD computation. The formula above refers to square of the distance measured by maximum mean discrepancy. The synthetic set, condensed through distribution matching, is optimized by minimizing this formula. In this formula, the network parameter theta follows p theta 0, and phi theta refers to randomly initialized networks. Distribution matching used randomly initialized networks to obtain various embeddings for MMD estimation. However, the network parameters are sampled from a simple predefined distribution, resulting in a limited number of patterns, which represents only a small fraction of the hypothesis size. This paper, Improved Distribution Matching for Dataset Condensation, solves these shortcomings via 3 novel techniques: partitioning and embedding augmentation, efficient and enriched model sampling, and at last, class-aware distribution regularization. In this section, I will introduce the methodology of IDM. The first novel technique of IDM is partitioning and expansion augmentation. Since shortcoming 1 arises due to the small size of S, it is difficult to contain all the features of tau. IDM addresses this problem by applying partitioning and expansion augmentation to the synthetic sets. Through this method, the number of features from S is increased. In more details, let's say that Si is an image of the synthetic set S. First, IDM partitions Si into L times L equal pieces. Then, IDM expands each piece to the original size of Si using differentiable augmentation. This process can be described by the formula shown in the slide. In this way, the number of features extracted from S increases from S to L squared times S. The second novel technique of IDM is efficient and enriched model sampling. To address the second shortcoming of distribution matching related to unvalidated embeddings in MMD computation, IDM extends the parameter theta, which originally followed the probability of p theta 0 to now follow p theta t. Here, p theta t represents the intersection of p theta 0, p theta 1, and so on up to p theta t. P theta t refers to the parameter distribution of models initialized with p theta 0 and trained for t iterations. Through this approach, the sampling of theta is enriched by adding a new dimension, training iterations. This leads to a significant diversification of the parameter distribution and provides more informative features for data condensation. However, there are computational resource challenges when saving each trajectories of p theta t. To address it, IDM proposed a novel data structure to enable an efficient model sampling, called the Memory Efficient Model Queue. In this Memory Efficient Model Queue, there are 4 operations: push, pop, train, and sample. Push adds a newly initialized model phi theta to the queue, where the parameter theta follows the distribution p theta 0. Pop removes a model from the queue if the size of queue exceeds the maximum capacity n. Train fetches a model from queue at random and trains it using real data for k iterations. Sample randomly selects a model from queue for use. This is how the model queue works. The push operation initializes the queue and maintains model diversity by periodically adding newly initialized models to the queue. Pop manages the size of the queue, controlling IDM's computational cost. Train retrieves intermediate model parameters theta t during training. Sample selects theta from the distribution p theta t for dataset condensation. P theta t can be visualized as a matrix with rows representing samples from p theta 0 and columns representing training iterations. Unlike distribution matching, which samples from the first column, the model queue dynamically traverses the matrix from left to right and top to bottom, balancing training iterations t with computational resources. Train handles the left to right traversal, while push and pop manage the top to bottom traversal. However, even with efficient and enriched model sampling, the second shortcoming of distribution matching has not been fully overcome. While the extracted features from the original dataset was scattered, only their means were matched. This resulted in a failure to match the higher order moments between the real and synthetic distributions. Additionally, the scattered features became mixed and less distinguishable for classification purposes. Consequently, the performance of the synthetic dataset remained poor. As a solution of this problem, IDM introduced a classification loss as a regularization term to the synthetic distribution, making the extracted features more distinguishable. For classification, IDM uses networks sampled from the model Q, but since each network has different training steps and different accuracies, IDM multiplied the accuracy of sampled network by the classification loss to address this issue. The overall loss function of IDM is designed as follows. It is the sum of the distribution matching loss, where the network follows the distribution of p theta t, and the modified classification loss. Additionally, a weighting parameter is applied to the classification loss. This is the overall framework of IDM. Images in the synthetic set are first partitioned and expanded, and then, along with images from the real set, fed into the model sampled from the efficient and enriched model Q. The matching of output distributions is regularized with the class-aware distribution regularization. This is the pseudocode of IDM. The input of this algorithm is the training set tau. The algorithm uses 7 parameters: phi, p theta 0, q, n, maximum of n, k, and m. In the first step, the q is initialized with n randomly initialized models phi theta I, where theta I follows the distribution p theta 0. The loop repeats m times. In each iteration, a network is sampled from Q and its accuracy is calculated. The distribution matching loss and classification loss are computed using the network phi theta. The synthetic set S is updated by minimizing the total loss. Next, to maintain the model Q, the network phi theta is trained for k steps and then placed back into the Q. A new model phi theta 0, where theta 0 follows p theta 0, is pushed into the model Q. If the Q size exceeds the maximum value n, a model is popped from the Q, and the loop goes to the beginning and repeats. After m times of repeat, the condensed set S is produced as the output. This is the synthetic set generated using IDM with the C400 dataset, where there is one image per class. You can observe that each synthetic image was partitioned and expanded using augmentation into 2x2 sections. Each image within the black bold lines represents a different class in C400. In this section, I will present the experimental results of IDM. The author used 6 datasets to compare IDM with previous methods: MNIST, Fashion MNIST, C410, C400, Tiny ImageNet, and subsets of ImageNet consisting of 100 categories. Various methods were used for comparison. For core set methods, they used random selection, herding, and forgetting. For previous dataset distillation methods, DD and LD, which laid the foundation for dataset condensation, were included. Additionally, optimization-oriented dataset condensation methods such as DC, DSA, and CAFE were used, along with dataset condensation via distribution matching. This table shows the results of dataset condensation methods, including IDM. As you can see, IDM outperforms not only the original distribution matching method, but also the optimization-oriented dataset condensation methods. The author conducted an experiment comparing the performance of trained models versus random models. They used 600 pre-trained confident models on C400, trained for 10, 20, up to 60 epochs for 10 IPC condensation. As shown in the following graph, sampling both pre-trained and random models, which is a method used in IDM, demonstrated the best performance. Additionally, the pre-trained models outperformed the random models. Next, the authors examined whether the classification loss actually improves the performance through an experiment using C400 with IPC10. They measured how the consistency ratio changes as the number of nearest neighbors increases. The consistency ratio refers to the proportion of each synthetic sample's real image neighbors that belong to the same class as the synthetic sample in the feature space. As shown in the graph, sampling both pre-trained and random networks improves the consistency ratio compared to the original distribution matching method. Additionally, IDM's regularization method further improved the consistency ratio, indicating more clearly classified features. This result demonstrates that IDM has effectively alleviated the class misalignment problem in distribution matching. Next part is the ablation study. The author demonstrated the effectiveness of each component by adding the 3 ideas of IDM successively. First, with model sampling. Next, with model sampling and distribution regularization. Finally, with all 3 novel ideas, model sampling, distribution regularization, and augmentation. The results showed improved performance on both CVPR100 and ImageNet subsets. The authors varied the architectures used in data condensation and the evaluation of the synthetic dataset to examine how the performance was affected. The 4 architectures used in the experiment was ConvNet, AlexNet, VGG, and ResNet 18. IDM with ConvNet showed the best performance regardless of the evaluation model architecture. Additionally, dataset condensation using more complex architectures such as ResNet performed worse. This may be due to challenges in optimization and noisy extracted features. Lastly, let's move on to the conclusion. The paper proposed an improved distribution matching method for dataset condensation. IDM identified 2 key shortcomings of distribution matching. First, the imbalance in the number of features between tau and S, and second, the use of unvalidated embeddings in maximum mean discrepancy computation. To address these issues, IDM introduced 3 novel techniques. First, partitioning and expansion augmentation. Second, efficient and enriched model sampling. And at last, third, class-aware distribution regularization. Through various experiments, IDM demonstrated a significant improvement in performance. Thank you for listening to my presentation.